All right, so we are in the second to last lecture of linear algebra. And of course, these last three on chapter 7 are kind of the more abstract sort of pinnacle, what we've been trying to thunder up to with all of our discussion of Rn and all the concepts thereof. Right. So the concepts themselves have remained the same. Right. We know the notion of a vector space is a set that satisfies 10 axioms. Subspace is the same as it was for Rn in the sense that it has to be closed under addition and scalar multiplication, and you have to have the zero element in there. And so now what we want to do is extend our discussion to span, linear independence, basis, and dimension, all of the key concepts that we talked about for Rn. All right, and so the focus of this lecture is on span and linear independence. All right, so we know, okay, we'll state this in general, but then notice the similarity to what we've already discussed in Rn. Take a set of vectors in a vector space V, right? So what we've been doing is taking literally, if we were in R3, we took vectors that had 3 components, and think of that as a prototypical example. But remember now, for vector spaces, they could be spaces of functions, they could be matrices, they can be sequences, who knows what they are, as long as they satisfy those axioms. And so we define the span of a set of vectors to be all, and this is key, finite linear combinations of the vectors in that set. So we didn't have to worry about that before because we only started off with finitely many vectors because we were in Rn. That was a finite dimensional space. Now, if you were talking about a set of functions or polynomials, it's not clear that you have to have only finitely many vectors that are required to span a particular set. But what we define the span to be is the set of all finite linear combinations of those. So you can find finitely many, or take any finitely many vectors in that set, multiply by constants, add them up, that will belong to the span. And that's true for all possible finite combinations. All right, so let's actually just look at these sets of polynomials and see just describe what they ought to span. Okay. And so here, if we just take the set containing the functions 1x and x squared, remember, there are only 3 vectors in here, so we don't have to worry about this finite business. You're only going to have finitely many to begin with. And so the span would look like any function that you can produce using constant C1, C2, and C3, right? And so those would be all the quadratic functions, or all the quadratic polynomials. So we take this for all Ci and R, right? So all the constants are real. That we already talked about. That should be P2, the set of all polynomials of degree at least 2, or at most 2 rather. If we continue onward, right, so notice here, if we clap on all positive integer powers of x, right, so now this is an infinitely many, or set with infinitely many functions in it, and we want to know, well, what does it span? Well, remember here, to be in the span, you have to be able to choose finitely many of those functions, multiply by constants, and add them up. But it doesn't matter which ones you choose, right? So I can generate a 1/millionth degree polynomial by just using x to the 1/millionth, right? Or I can use x plus x squared, right? It doesn't matter. Right, so here you could generate, if you think about it, give me any polynomial you want. A polynomial is a sum of finitely many constant multiples of these guys. And the degree is the highest power of any of those terms. And so all you'd have to do is choose the right finitely many of those guys, add them up, and to get that polynomial. And so this would be the set of all polynomials. So the span, if I took the span of that and span of this, right, that's the set of all polynomials. Okay. And now here, if we throw out the odd guys, now if you add any of those, you're always going to get an even power, and no powers are odd. So this would be, if you took the span of that set, it's the set of all even polynomials. And by that we meant polynomials with only even powers in their terms. All right. So think about that. give me any even polynomial, you do the same thing here. You choose just the right finitely many terms that were in the polynomial itself, multiply by the correct constant, add them up, and that generates that polynomial. We don't have to use sets of functions. We can talk about sets of matrices, right? And so for instance here, if I just take those four matrices in which they're all 2 by 2, and I'm just taking each time one element or one entry in that matrix to be 1, everything else is 0, right? So here, if I were to take finite linear combinations of these guys, right, so I multiply each one by a constant. So each one of the, I don't want to rewrite every time, but I'm just multiplying each one of those by a constant. You could, since the CIs are real, you can generate absolutely any matrix you want with real entry, any 2 by 2 matrix you want with real entries, right? And so this span of this guy would be R2 cross 2, right? That is the set of all, that's what we labeled as the set of all 2 by 2 matrices with real entries. Okay. And this guy, this one we'll look at. It goes back to a homework problem, actually, in which you talked about the trace, right? So this would probably go back to 3.2, the trace of a matrix, right? So let me just recall here. So the trace, if I just gave you a 2 by 2, since we're looking at 2 by 2s, is just the sum of the diagonal entries, right? So if I just add those guys, that's the trace. And so notice here, if I look at just these three matrices, the trace of each one of those is 0, right? Furthermore, if I multiply any of them by, if I multiply them all by constants and add them up, right, you're gonna, if you multiply this one by C, let's say C1, C2, and C3, you're gonna get 0C1, 0, 0, plus 0, 0, C2, 0, and then plus C3, 0, 0, negative C3, or that would just be what that would be a generic element in the span of those three matrices. And then we add component wise, you'd have C3, C1, C2, negative C3. That would be that general matrix. And notice its trace is 0. Right, but that's as general as you can get if you multiply by any real number C1 through C3. And so the span of this set would be the set of all 2 by 2 matrices with a 0 trace. Right, the only way you're going to get a 0 trace if in a 2 by 2 is to have an entry and its additive inverse on the diagonal, because you only have 2 elements to play with. And so this span of that guy would be that set, or that vector space. This is a little bit kind of perhaps premature, but kind of a flash forward. Each of these guys, we have to talk about the notion of linear independence, but they seem like exactly what you would need, bare bones, to generate each of these vector spaces. So it's conceivable that the bases for each of these spaces are precisely these sets that I've listed here, right? And so thinking ahead, if we can somehow show they're linearly independent, whatever that means, right? We'll have to look at that definition. Then they would be minimal spanning sets. They would be bases for these vector spaces, and the dimension of the space would coincide with the number of elements in the basis, just like it would have in Rn. So if this were true, this P2 would be a 3-dimensional vector space. P and the set of even polynomials would be infinite dimensional. This guy would be 4-dimensional and then 3-dimensional. All right, so just kind of flash forwarding a bit. All right, I omitted this guy, okay, because that one actually is linked to complex eigenvalues, and we didn't talk about complexes. So you can omit part C. Okay, good. So just as it was in Rn, if I take any non-empty subset of a vector space, so I take any number of vectors you want and take its span, whether or not it actually spans the whole space is irrelevant. The span of those set of those vectors is always a subspace in its own right. All right, and that's a true fact. We don't have to prove that. That is a true statement. Okay, so let's look at this. We have a set of two vectors in P2. So polynomials in P2 would be quadratic polynomials. And we want to know two things. Does this function belong to the span of S? Right? So can you write it as a linear combination of those two elements of P2? And furthermore, does that set actually span all of P2? Okay, so let's see. So for this to belong to the span, what we're asking for is, are there constants C1 and C2 so that if I multiply each one by those constants and add them up, I get back this, right? So can I find C1 and C2 for which that's true? Let's actually simplify this. The only way two polynomials are going to be equal is if the corresponding coefficients of the terms of the same degree are the same, right? And so I'm going to distribute the C1 and the C2 through, and I'm going to collect like terms. That's times x, and then plus C1 plus 4C2 is that guy. All right, and so notice here on the right side, the coefficients of those guys are 1. And so what we get, in order for this to be true, we have three conditions that have to be satisfied. Namely, the C1 plus C2C2 has to be 1, right? This coefficient has to be that coefficient. 2C1 plus 5C2 has to be 1, same thing. And then C1 plus 4C2 has to be negative 1. Right, so those three things have to occur. Those three equations have to be satisfied in order for this guy to belong to the span of those two vectors. But notice that's just a linear system, right? So let's actually write it as such. 1, 2, 2, 5, 1, 4, bar, 1, 1, negative 1. And I want to see if there's a solution. Right, so let's put this into echelon form. I want zeros here and here, right? And so I'm going to multiply row 1 by negative 2, add it to row 2 and plug that into row 2. And I'm just going to subtract row 3 minus row 1 and put that into row 3. If I do that, what I get is 1, 2, 0, 1, 0, 2, 1, negative 1, negative 2, just following through the arithmetic. And then I want to put a 0 here to get this into echelon form. Or no, not necessarily. Yeah, actually, I'm right, because you want always, each row has to have strictly fewer zeros than the one after. And so I want a 0 there. And so I'm going to multiply row 2 again by negative 2, add it to row 3 and put that into row 3. And what I get is 1, 2, 0, 1, 0, 0, 1, negative 1, 0. All right, and so does this function belong to the span of that? Well, can we find constant C1 and C2 that work? Well, from here, we know that C2 has to be negative 1. And from this guy, C1 plus C2 has to be 1. And plug C2 in there. C1 minus 2 equals 1. And so C1 has to be 3. And so indeed, if you chose the constants this way, you can write this function as a linear combination of those two guys. So yes to this guy, that is in the span. However, does this set of vectors span all of P2? And the answer is no, right? Because what we know from R2 is that the minute you have a 0 row like that, you're going to have a condition imposed if I replace the right-hand side by a general vector, right? And so remember, this is just like in R2 or R3 or what Rn. You'd have those are your, you'd have these two functions on the left with c1 and c2. On the right, you would have b1 x squared plus b2x minus b3, right? And so you'd have b1, b2, b3 here. Within, there'd be conditions on here, right? So actually, let me just put that in. 2, 5, change back to the original guy. All right. And so you'd put this in echelon form like you normally would, and you would get a 0 and 0 here, but something that's not necessarily 0 there, right? So this would be an expression involving the BIs, right? So you get the same sort of thing here on the left, but the minute you have a 0 row here, that tells you there's going to be a condition imposed on the components of that vector. And so if you don't satisfy that condition, then that particular vector does not belong to the vector space. And so for choices for which that condition on B is not satisfied, this function does not belong to the span of those guys, right? And so it does not span P2. Okay. Now that stands to reason, because if you go back up here, we claimed that this set did span P2, right? And we actually hinted that this might be a basis for P2 so that its dimension would be 3. This set only contains 2 functions, not 3. And so if this were true, if the dimension of P2 is in fact 3, then 2 vectors can't possibly span it. Okay, there's that example. All right, so now let's go to the notion of linear independence. Again, the definition is the same as it was in our Rn space. All right, and so let's take a look. Take a subset, any subset of a vector space V. So you have a finitely many vectors or whatnot. So actually you could have infinitely many, right? So you can take infinitely many vectors in a vector space. And what we'll say is that those vectors are linearly independent of each other if you choose any m of them. So it doesn't matter what vectors you choose, just choose any number of them, finitely many. If the solution, if you multiply each one by a constant, add them up, if the only way to get the 0 vector is for those constants all to be 0, then the set itself is linearly independent, right? And that was the definition we used in Rn. We just didn't have to worry about the linear finite, or the finite number of the finite combinations, right? So there you were only ever taking finitely many vectors to begin with, and so that was a moot point. Here, it could be like that set 1x, x squared, x cubed, x to the fourth, dot, dot, dot. So there's infinitely many functions in the set. But what you have to show is that if you take any m of them, this holds, right? So you have only finite combinations to consider. Okay, so let's look at this, right? Are those 3 vectors linearly independent? Well, those were what we just looked at, right? So in the previous example, right, this was the 1 vector, 2nd, and 3rd. Those are the 3 vectors that we already considered. And what we said was that you could rewrite x squared plus x minus 1 if you used c1 to be 3, right? So you had 3 times the first guy and -1 times the second one. This was a true statement. And so these are linearly dependent, right? If you were to take everything to one side, so you have 3 times this first guy, plus 1 times the second guy, plus 1 times the third guy is equal to the 0 element of P2. Remember, the 0 element of P2 is the 0 function, the constant 0 function. Notice that you have 3 distinct functions, so that if you multiply them by just the right constants and add them up, you get the 0 constant back. And so by definition, this equation, or this expression on the left, is 0 by choosing C1, C2, and C3 not to be all 0, right? So there's a way of generating the 0 vector without having to have all those constants be 0, is what I'm trying to say. And so these are dependent. If it were the case that the only way to generate the zero constant here is by making all those guys zero, then they would have been linearly independent in that case. Okay, and so this is kind of a consequence of that. We know that a subset of a vector space is linearly dependent if and only if one of the vectors in S is in the span of the others. And that's what we've already proved this in example 3. We show that this guy belonged to the span of those two vectors. And so that's what built the dependence in. Okay, let's try these. Right, so we have four functions in P3. P3 is a set of all cubic polynomials. And we want to know if they're linearly independent. Well, by definition, that means if I multiply the first by C1, the second by C2, the third by C3, and the fourth by C4, and I want to see if it's the zero constant function again, right? So again, this generates a system. You have to group the x cubed, the x squared, the x, and the constant terms together, right? So let's do that. I have C1 plus 3C2 x cubed plus I have a C2 plus C3 x squared. So I'm just multiplying the C guys through and then grouping like terms together. Plus 2C3 plus C4 times x, and then plus C4 is equal to 0. Right, so distribute the C's through, add like terms, and then factor out the x squared, x cubed going up. Okay, the only way that's going to be 0 is if the corresponding coefficients of the x cubed, x squared, x, and constant terms on that side are 0. Well, for the 0 function, all those are constants are 0. And so what we get is the system C1 plus 3C2 is equal to 0. C2 plus C3 is equal to 0. 2C3 plus C4 is equal to 0. And C4 equal to 0. Okay. I wanted to line it up a little bit better. Let me actually do that a little bit better. Right, so I have C1 plus 3C2 equals 0. And then I have C2 plus C3 equals 0. Then I have 2C3 plus C4 is equal to 0, and then C4 equals 0. A lot of this sometimes, if you write it like I just did before, it's not clear as to what's happening. If you write it in this form, it's a lot easier to see what's going on. I'm not even going to bother changing this over to a system. It's easy to see what the solution is just by back substitution. C4 is 0. So if C4 is 0, plug that here. If that's 0, then 2C3 is 0, so C3 is 0. But if C3 is 0, plug that here, then C2 is 0. And then same way, C1 is 0. So the only way this is going to hold is if they're all 0. Right, so hence, the vectors are linearly independent. All right. Okay, and then now let's look at this. We have a set of, how many vectors do we have here? How many functions? We have 1, 2, 3, 4, and 5 functions. All right. So if you look at this now, we're going to have, remember the 0 element here is 0x cubed. All right, so if we were to go through, you'd have C1 plus C2. You multiply each of these guys by an appropriate constant. So I'm not writing all of it out. Just take each function here, plop it in one of those parentheses. This is equal to 0x cubed plus 0x squared plus 0x plus 0. Huh? All right, so now notice that once you group the x cubed, the x squared, the x, and the constant terms together, you're going to get 4 equations, right? One for each of these coefficients being equal, but you have 5 variables, right? You have a C1 through C5. And so the minute you have 4 equations in 5 variables, that means that there exists a free variable, right? And so if there's a free variable, that means that the system has infinitely many solutions. In particular, it has more than just the trivial solution where all the c's are 0, right? So this implies there exists a solution, right, to this equaling 0 that's other than all the ci's equaling 0, right? And so those functions have to be linearly dependent in that case. Okay. All right. Ooh, now look, we have, so before we had functions, now we have matrices. We want to know if these guys are linearly independent and if they span the set of all 3x2 matrices. All right, so first things first, let's actually look at, to span one of these, let's let M equal M11, M12, M21, M22, M31, M32, right? So that is a generic matrix in a 3x2 matrix. And so what we want to know is what matrices, right? So what does it mean for those 3 matrices to span this? It just means, or to span all of the set of all matrices of 3x2, it means that I can multiply this guy, right, by C1, multiply this guy by C2, and the last guy by C3, and I should get this vector, or this, I'm sorry, this matrix. Okay. On the left, however, we can actually simplify that, right? So if I multiply everything through here by C1, by C2, and by C3, what I'm going to get is the following, and I'll let you actually follow through on this. So if I were to multiply those through, right, I'd add component-wise. So multiply through, add them component-wise, and then set corresponding components on this side equal to that guy, right? So the matrix you get on this side would be, let's see, how do I want to write this? 1, 5, 3, right? 2, 4, 3, a 0, 0, 1, 1, 1, 5, 3, 1, 4, 2, and 4, 10, 3. Right, so I remember I'm getting 6 equations, right? So from here, let me just show you what I'm doing. From the first one, I have C1 plus 5C2 plus 3C3 is equal to M11. And then I'd have the next equation, I'd have 2C1 plus 4C2, I'm looking at this one, plus 0C3 is M12. And I keep doing that. For that guy, I'll have 6 equations, one for every entry on this side. And so the system I'm getting on the left side, I have 6 rows and 3 columns, and the coefficients of the C1, C2, and C3 are listed in that order. The augmented matrix, of course, would have a bar with the M11 through M32 down below here. All right, but remember, I don't need that particular right side. Everything is characterized by writing this guy in echelon form and seeing if there are 0 rows, and then also seeing if there's a solution that puts a particular vector in its span. All right, and so let's look at this. If I put this into echelon form, oops. All right, so here's the matrix. I have 1, 5, 3, 2, 4, 0, 0, 1, 1, 1, 5, 3, 1, 4, 2, 4, 10, and 3. Okay. And so now I'm just going to put zeros here, right? And so I'm going to apply the appropriate row operations to do so without writing them all out. And so I have 1, 5, 3, 0, -6, -6, 0, 1, 1, 0, 0, 0, 0, -1, -1, and 0, -10, -9. Right, so just the appropriate row operations on those 4 rows to put zeros in those first entries. And then I'm going to basically add rows 3 and 5 and put that into row 5. Then I add rows 2 and row 3 and put that into row 2. And then I'm going to move all the 0 rows to the bottom, right? That would put it in, at least into the right form. And so if I do that, I get 1, 5, 3, 0, 1, 1, 0, 0, 1, and then I have 3 rows of zeros. Right, so I'll leave that to you. By now we've done this so many times, it's probably second nature, right? But remember, all the 0 rows have to go at the bottom to be in echelon form. And then the only thing we'd have to do extra is take care of this guy. That's what happens here. Okay, and so here, notice we have two things that are happening. One, remember, we're multiplying this by C1, C2, C3 each time around. And so from the top part, remember the first columns for C1, C2, and then C3, we have C3 is equal to 0, C2 plus C3 is 0, but if C3 is 0, so is C2. And then we have C1 plus 5C2 plus 3C3 is equal to 0, but C3 and C2 are both 0, which means C1 is. Right, so first thing that we can conclude is that when we look at these vectors and we set them, if this were the 0 vector on this side, so the 0 matrix, right? So if we chose all those m's to be 0, that means that we have all zeros here. The only way to produce the 0 element of R32, namely the matrix with all zeros in, is for C1, C2, and C3 to be 0. All right, and so the answer to the first one is, or for this part, is that these vectors are in fact linearly independent. All right. Now, do they span all of R32? Right, so this one means the 3 matrices in S are linearly independent. Sorry about that. Okay. Now, do they span all of R32? And the answer is no. Right, so the 0 rows imply that S does not span all of this. And what we'll find is that the reason is the dimension of this space is 6, right? It's the dimension is obtained by multiplying the 3 and the 2, right? And so 3 vectors can't span a vector space of dimension 6, as it turns out. But you don't need to know that. You just need to know 0 rows implies it does not span, just like it did for the Rn case. All right. So quick recap on that, right? Just to make sure that we have the notion down, because I don't want you to get caught up with the computations, right? You have a set of vectors in a vector space, and you want to know if they're linearly independent. What you do is you multiply each of the elements by a constant, C1, let's say, C2, C3, add those up, and set that sum equal to what the 0 element in that space is. The 0 element of this space is a 3x2 matrix for which all the entries are 0. Okay. Once you set that equation up, you simplify it to get a system of equations that you can write, or then for which you can extract a matrix. You put that matrix into echelon form, and then try to use that to see what the values of the C1, C2, so on and so forth are. If they are all 0, then the original vectors that you looked at in the space are linearly independent. If you can find solutions for which at least one of them is not 0, then those vectors are linearly dependent. Second question, do those vectors span the whole space in which they are being pulled? And that simply falls on if there are 0 rows or not. If there are no 0 rows, it spans. If there are 0 rows, it does not. Plain and simple. That's a true statement that process remains the same whether I'm using sets of matrices, sets of vectors, sets of sequences, what have you. Okay? Same process. All right, let's look at example 7. All right, so your favorite, we can't escape trigonometry, right? So we want to know whether or not these vectors are linearly independent, right? So we want to ask, can one be written in terms of the others, right? So if you remember, without going through all that formally, remember that sine squared of x is equal to 1 minus cosine 2x over 2, right? There's that double angle formula in disguise. And I can rewrite that as 1/2 minus, and that's 1/2 times 1, minus 1/2 times cosine of 2x, right? So if I write it in that way, notice I wrote that function as a linear combination of these two guys, and those guys are not both 0. So these functions are linearly dependent. Okay, so you don't have to go through and form a matrix all the time. If you can see right off the bat with what functions you're dealing with and formulas you know, if you can rewrite one as a linear combination of the other, then dependence falls right out. The question now is whether or not they span all the set of all continuous functions, right? So you take any function f that is continuous on R. So it's defined everywhere on R. So the domain is R, right? And it's continuous. Well, my claim is this was not easy. So the claim here is that it does not span all of the set of all continuous functions. And for instance, x does not belong to the span of these guys. All right. In fact, here, since we have if this guy is a linear combination of those, the span of these three vectors is equal to the span of those two, right? You're not adding anything by clapping that in. And so here I don't have to consider the sine squared in there. That's why I do span of those two. Well, remember, what this means is that you have to be able to find constants C1 and C2 for which this holds. But that has to be true for all x and r. That's the key here. These are functions of x. And so as a function, for every value in its domain, this equation would have to hold. And the problem is, well, let's take a couple values, x equals 0 and x equals pi, for instance. If x is 0, cosine of 0 is 1. So we get C1 plus C2, 0 on that side gives you a 0. And for x equal to pi, we'll plug that in. Cosine of 2 pi is also 0. So you get C1 plus C2 is equal to pi. But if you subtract those, this is equivalent to saying that 0 is equal to negative pi, which is false, right? So there is no way, even if you just consider those two values of x, there's no way to find two constants to multiply these two functions by on the left so that they always produce x when they're added together. And so this means that S does not span the set of all continuous functions. All right. What it turns out does span it is the set of all positive integer powers of x and 1. So if I took the set 1x, x squared, x cubed, x to the fourth, dot, 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 that does span the set of all continuous functions. All right. And then finally, let's look at a space of infinite sequences, right? So the sequences that I'm looking at is, let's see, the set of all, let's see. Yeah, okay, so what R infinity is, do two step by step. R infinity is a set of all sequences, infinite sequences, where the AIs are real. Okay, so give me any sequence you want where the AIs are real numbers. That collect them all together. That's what R infinity stands for. And then what I'm doing now is I'm forming a set S of sequences where each one of them has an initial amount of ones and then everyone else is zero. So for V1, I let the first entry be 1, then everyone there else is a 0. For V2, I let the first two guys be 1, and then everywhere else at 0. And I do this for every n. Okay, so I'm considering infinitely many sequences of this form, and I'm asking two things: whether or not that set spans R infinity, and whether or not these guys are linearly independent. All right, and so let's look. Right, if remember the 0 sequence here is the 0 element of R infinity. Okay, and so if they're going to be linearly independent, then the only way, so if I start adding these guys up, equals the 0 vector, so 0, 0, 0, 0, so on and so forth. So I'm going to get C1V1 is C1, 0, 0, dot, 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 plus V2 is 1, 1. So I get C2, C2, 0, 0, 0, right? Plus C3, V3 is C3, 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 and then zeros thereafter, and so on and so forth. All right, the only way, let's start from the first guy here. The only way I'm going to get this equal to the 0 vector is if C1 is equal to 0. Right? There's no way I can multiply these guys by, let's see here. Right. So eventually this ends, right? So eventually you have to take, remember what it means for linear independence is you take any m of them. So eventually that's going to end. Let's say it's CM VM, right? And so this is through 0. And then at the very end, CM, right? All right, sorry. So you have m of these guys, m CMs, then zeros thereafter. All right. And then what you get from that is a system of m equations. The first one is horrendous because you add all the constants together. That has to be the 0 element. But the next one, you're only adding the last m minus 1 of them together. And then for the next one, you add the next m plus m minus 2, all the way down to the very last one here. In the last element, you get Cm equals 0. Right? So if you just add the corresponding coefficients each time, the first ones are always there, so you get all of them. For the second component, that guy is 0, but everything else is there, so you get this sum, and you keep whittling this down until you get to the very last entry, which is 0. But the minute that's 0, if you use back substitution all the way through, you get that they're all 0. And so any finite linear combination of the guys in this set are linearly independent because the only way to get that to be the 0 vector is for all the constants to be 0. And that's true for all linear combinations. And so the set is linearly independent. As for whether or not it spans R infinity, remember, to be in the span of R infinity, you have to take, every vector has to be able to be written as a finite linear combination of the guys here. Well, for instance, take A to be just the vector 1, 1, 1, 1, 1, 1, and it never ends. Right? So all coefficients are 1. All of the components are 1, rather. If you take that sequence, there's no way to only use finitely many of these guys to generate it, because eventually, after some point, there's 0. Right? And so even if I took the one that had 1 billion the first 1 billion terms are 1, that's fine, but the 1 billionth and first term is going to be 0, and that can't possibly generate that sequence. So this does not belong to the span of S. And I'm going to put here Y, right? I want you to convince yourself of that. But the key is there's no way to use it cannot be written as a finite linear combination of the vectors here, because all of these guys after some point are zeros, right, in their sequence. And so just take the one that has the largest index. The m plus first term would be 0, not 1. So they can't be in the span. Okay, so yeah, this section is a lot to chew, a lot to get through in some sense. On the upside, the concepts are identical to what we did in RN. It may not look it here because the implementation requires that we use functions and matrices and sequences, but the concept, what you're trying to prove, is exactly the same as what we were doing in RN. All right, so grapple a little bit with this with the homework and the concept checks. We have one more to go, and that is we kind of already hinted at basis and dimension, but we'll end on that note in the next lecture. Okay, hang in there, and we will get to the next one soon. All right, take it easy.